Welcome back to the TI corner of the room. We have my TI 980 mini computer down here, and we're starting to make some progress on it. The power supply was just way too rusty and completely obliterated, so we ended up rebuilding it completely from scratch using modern mean wells. And after we did that, we're seeing something. We got a couple of lights turning on the front panel, but the CPU is clearly not running. And after a little bit of probing, it seems that the clock is not propagating throughout the system. So there's something holding that clock low. And I think we're going to dig into that this upcoming Friday night on the Twitch stream. If you want to join us, there's a link in the description below to the Twitch channel. If not, all the Twitch streams are recorded and I upload them to a second channel called Usagi Workshop. And if we can get this TI 980 starting to come to life and do some CPU type things, we're going to then get to work on this ASR 33 and get it hooked up to the 980. And this is a project that I'm very excited about because I love old clicky clacky teletypes like this. But that's not what we're here for today. In this video, we're here to talk about this guy right here, which is my TMS 9900 homebrew project that we've been building up. And it's been a while since we were on this one, a little over 2 months, I think. We put it down because I really needed to get that LGP21 up and running for VCF Southwest. And VCF Southwest came and went. The LGP21 ran for all 3 days without fault. It was absolutely stunning. But now that we're back home, it's time to get back into this project. However, it's been so long since the previous episode, I've kind of forgotten where we left off. I actually had to re-watch the previous episode in the series just to kind of get my head in the right space. So let's take a moment, walk through all of the boards that are on here, and bring ourselves up to speed on what exactly has gone wrong and how we're gonna fix that today. Right up on the front here, we have our TMS 9900 CPU. Just behind that, we have the TM9904 that is generating the special clock for the CPU, as well as a bunch of headers so that we can do pull-ups or pull-downs for certain signals on the bus. Right behind that, we have 2 kilowords of ROM, and currently this contains all of the interrupt code as well as the basic assembly that we're using to test out the serial communication on the device. But ultimately, this is going to contain a bootstrap loader to load in whatever program is in the cassette mag tape or whatever it is that we ultimately end up using for long-term storage and copy that into RAM. And right behind that ROM is the address and control for it, as well as a power on reset and reset button. Then we have a little connector that connects the frontmost backplane to the middle backplane, where we have the address and control for the RAM, as well as a bunch of status LEDs on the top. And then we have 3 boards making up 6 kilowords of RAM. Now remember, 1 word is 16 bits, so that's a total of 12 kilobytes. And 6 kilowords is not a huge amount, but it's also not an insubstantial amount. Also, this is really fast static RAM, so we don't have any wait states trying to access it. Now, connecting the middle backplane to the back backplane is this interesting double stacked buffer board. This was a late addition that we did in the previous episode because the CPU is going to be trying to assert the address bus for everything that's on that address bus, as well as the data bus and everything. So we just put some 74LS245s on there to kind of isolate the CPU from the rest of the IO system. However, I think all of our problems are stemming from this late addition here. I did not originally design this with buffers in mind, and well, it created some serious problems that we're still fighting the ramifications of. But behind those buffers comes the third and final backplane on this left side of the board here. The first board in that backplane has all of the address and control for the serial communications and parallel port. The next 2 boards are the 2 serial boards that each have a UART and a baud rate generator on them. The first one is hardwired to 300 baud. That's going to go to our little TI Insight Series 10 terminal on the top here. The second one is hardwired to 1200 baud, and we can send that off to a second terminal for multi-user stuff. The fourth and final board has a parallel port on it that can go to a printer, or at least that's the hope, as well as the logic for controlling interrupts. Now, we had tested out the UART a little bit on a breadboard, and we got it doing exactly what it was supposed to do. But when I built it out on the PCBs here, nothing worked, and we had a litany of problems. First of all, there were 2 bugs in my assembly program. After fixing both of those, we discovered that there was a weird bug in the assembler that resulted in bad binaries. I also had a pull down on IC0 and I needed that to be a pull up. Then we noticed a weird high resistance connection between the tape interrupt line and ground on the backplane. Turned out there was a tiny little fleck of copper between the traces, and all it took was an X-Acto knife to clear it. Then we're getting into the trouble of the buffer boards. I had them initially wired up for the wrong direction, and then one of the 74LS245s had a floating enable pin. This was just a simple layout fault. However, despite fixing all of that, it still didn't work, and that was where we left off in the previous episode. But I am like 98% certain that all of our problems are still on those buffer boards, and I think it has to do with where they are physically located. If we take a look at the schematic of those buffer boards here, you can see that it's really just 4 74LS245s sitting on the address bus and the data bus. Now on the address bus, we're hardwiring them in a single direction, coming from the CPU towards the I/O boards, because the I/O is only ever listening to the address bus. Now, if we look at the data bus, the 74LS245s can go in either direction. And so their direction is being controlled by the CPU directly using the DBIN pin. The only problem here is that the CPU also asserts DBIN when it needs to retrieve something from ROM or RAM. So whenever the CPU is trying to fetch an instruction from ROM, the LS245s are coming alive at the same time and just blasting the bus. So the CPU can never actually pull in an instruction from ROM and execute it, which is why absolutely nothing works. Now there's 2 ways to fix this problem. The first is to move the buffers from where they are, because they're quite far. They're on the other side of ROM and RAM. And if we move them to in between the CPU and ROM and RAM, that solves the problem. But that is an impossible thing to do because ROM is shared on the same backplane with the CPU. So I would have to completely redesign all of my backplanes and card layouts, and it's not a feasible solution. So the other solution that we're going to do is we're going to control the 74LS245s to go into a high impedance state whenever we're not in the I/O address range. And so I've actually separated this out between address and data bus. And we're gonna have to put those in 2 different locations because I'm just flat out of space. The first is the address buffers, and those are gonna go between the frontmost backplane and the backplane that contains all of the RAM. It's just 2 74LS245s that are hardwired for a specific direction, and that's it. But the data bus problem is a bigger one that's a little more difficult to solve. And I've got the schematic for it here. And the first thing that you'll notice is that there's only one 74LS245 on here. And that's because, well, the I/O is only working on 1 byte at a time. So there's no real need to buffer up the low byte. It's only going to be operating on the high byte. But we have to create some new logic to control the chip enable of the LS245, so that way we can send it into a high impedance state. We have 2 NAND gates that are looking at the topmost 4 bits of the address bus, and these are going into 2 NPN transistors that are creating a sort of TTL OR gate. This was the most compact way I could think of to make an OR gate that had really good high and low logic levels. This goes right back over to the 74LS245 and controls the direction. Now, if I put all of this in there, that theoretically should get the buffers moving correctly and everything should work. So I've actually gone through and machined those out. I've got them right here, and they're pretty interesting stack designs like the previous one. This is the address buffer board, and the 2 74LS245s are right here. I had to stagger them onto 2 boards that stack on top of each other because there just wasn't enough real estate to hit all of the address lines and have both of the LS245s on there. So the way that this works is that these long ones here plug into the actual backplanes to connect them to each other. And then there are these extra long pins on top of this one. and this little board right here pushes straight down onto those pins, making all of the connections. And then this is the data bus buffer board here. The 74LS245 is right here, but because the chip was a little too long, it covered up some of the lines that need to actually cross through on the bus. So we've got this extra little piece right here that's going to be on the second level, passing those lines through. And then all of the logic for controlling the high impedance state of the LS245 is right here on this little guy. We've got just a 74LS00, and then our two NPN transistors to create the TTL OR gate. And all of that, just like the previous one, will sit on these extended pins that push out the top, just like that and like that. But also, again, like the other one, I need to solder in the 5 wires for power distribution coming from the power supply right there. And then that whole combination will go in between the second backplane and the rearmost backplane. It was a proper challenge to get those buffer boards in place. I've learned some very valuable lessons about how to create interconnects on this project, which is good because when I get into UE2, a lot of the stuff I learned here is going to have to be implemented much better on that one. But I think I've got everything in place. Here goes. To be clear, I absolutely do not expect this to work, but the first step into figuring out why it doesn't work is right here by flipping that power switch and seeing what happens. So we'll just go ahead and flip the power switch on. It came out of reset at the very least. None of that, it's not working, but that could be because I have RX and TX backwards. I just kind of took a guess. I couldn't remember how it was wired up. So let me switch those around and we'll give it another shot. All right, round 2, we'll put the power switch on. Came out of reset and yeah, still doesn't work. Yeah, all right, so it's time to break the scope out and figure out what's still broken. All of the following footage is from 2 marathon troubleshooting sessions that spanned most of Thursday as well as our Friday night Twitch stream. I still had a colossal amount of things wrong, so let's just get stuck into it and fix everything we can find. The first thing I noticed is that I had an incorrect wire wrap jumper on the backplane. Removing that got the buffers working better, but didn't fix it ultimately. So let's sanity check that the UART is healthy. I'll pop the TR1602 out and put in an IM6402, which is pin compatible except for the negative 12 volt supply. Thankfully, I can disconnect that with a simple wire wrap jumper. That didn't change anything, but got us headed down a new path. Pin 16 of the UART is a status flag disconnect. If this pin has a high level, it disconnects the parity error, framing error, overrun error, transmit holding register empty, and data ready signals, allowing them to be bus connected. I had that tied permanently high, but I actually need the THRE and DR signals. Our code was never doing anything because the status bits were disconnected. I used a little bit of solder braid to clear out the solder, then used a pair of very sharp side cutters to slice the trace and soldered in a jumper to ground instead of 5 volts. That fixed that problem, but now we're jumping to the wrong interrupt levels. Looking closer at the 74LS148 that we're using as a priority encoder, we could see that it was sending us to level 6 instead of the level 3 it should. 6 in binary is 0110, and 3 is 0011. The most significant bit is pulled low and not affected by the LS148, so now it's 110 versus 011. I see what's going on here. I got bits 2 and 0 wired up backwards. At any rate, let's pull the encoder board out and make the bodge. This one was fairly easy to do. I just needed to remove a jumper, cut a trace with those super sharp side cutters, and solder a new jumper in place. I cut it a little long and it's got this weird kink, so hopefully the electrons figure out the right racing line through there and clip all the apexes correctly. Getting everything back into place and still no joy. Interestingly, the cursor is doing things that look strange though. The camera doesn't quite pick it up right, but it's definitely bad in a different way now. This is 100% on me and not knowing how to write code. Our status bits are gated by NAND gates with Schottky diodes to turn them into open collector gates. This means that they can't pull the bus high, they can only pull it low. But in the code, I am ANDing the status bits with a mask and then doing a JEQ, which is a jump if equal to 0, and that's backwards. I need to check if the status bits aren't asserted. We can fix this easy peasy by changing to JNE, or jump if not equal to 0. But this illuminates another problem. The 74LS245s don't have internal pull-ups, and open collector gates need a pull-up for the direction that they can't pull. So I've got to add 2 pull-ups on the I/O side of the buffer for the 2 data lines that the status bits affect. A little more bodge work, and oh, I just remembered, I need to order more of this MG Chemicals solder wick. I'm running pretty low. Okay, we're not there yet though, but this is excellent news on the scope. The trace to pay attention here is the red trace. That's probing the M0 stat line. This is an MMIO address that the CPU hits to check the status bits of the UART. If we look at the code, we hit that twice, which means that the CPU is seeing the interrupt request, jumping to the right location, checking the status bits and seeing them correctly, executing the read and echo code, then resetting the interrupt request and clearing the status. That's perfect, except instead of echoing the character that I type back to me, all it ever sends to the terminal is a tilde. No matter what key I press, all I get back is the same character. We can actually verify this on the scope. The green trace is the RS-232 in, and the yellow trace is the RS-232 out. After some hunting, I feel kind of super dumb on this one. See that green V? It should look like the yellow square. Earlier on in troubleshooting, we found an interesting problem with the receive register disconnect signal. On the MMIO decoder board, it goes through a 74LS04 inverter. This signal then goes to the RRD input pin on the UART. But that was backwards from what we needed for the DRR input pin, which is the pin that resets the data received signal. So thinking that I was being clever, I used a little transistor to re-invert the signal. Turns out that the RRD signal is also the wrong way around. So yet again, thinking that I was being clever, I just tied pin 4 and pin 18 together. But that means that the MMIO signal goes through a double inversion. And while the first 74LS04 is very fast, my little transistor inverter here is very slow. So slow, in fact, it can't keep up, and the CPU grabs an empty bus instead of the actual byte. The solution is what I should have done in the first place. I just removed the transistor and bypassed the LS04 inverter. I plugged it all back in, and victory! Or not. That's supposed to be the quick brown fox jumps over the lazy dog. Instead, it's so close, but still so far away. We actually have some letters right in there. If we look at the word brown, the first 2 and last letters are correct, but the O is coming back as N and W is giving us V. O in binary is 1001111. N in binary is 1001110. I'm starting to see a little bit of a pattern here, but let's see if it holds up. W in binary is 1010111. V in binary is 1010110. Yep, our least significant bit is stuck. But why? We double-checked everything on the UART board, and it's all working correctly. Nothing else is touching that data line except, oh, that data line also goes to the parallel port for the printer. The printer busy signal from the printer comes into one input of a NAND gate, and the other input is the MMIO signal to gate whether that busy signal goes onto our data line that's getting stuck. The first problem here is that the MMIO signal needs to be inverted. Right now, it's trying to check the status of the printer all the time, which is bad, but shouldn't cause a problem because our printer isn't busy. Actually, our printer isn't even connected, and that's the second problem. The other input to that gate is now floating. If I pull it down with a little jumper, it fixes the problem. All it needs is a pull-down resistor on the input from the printer and a little extra inversion slipped in, and after all of that, check it out. I have a multi-user typewriter. But it works. If I come over here and type on this data terminal, it shows up over there. If I type on this data terminal, it shows up over here. I can hit them both at the same time, and the CPU just handles it. This one's at 1200 baud, that one's at 300 baud. It doesn't miss a beat. Now, of course, this is not the finish line. I want to have similar functionality to the Data General Nova 1210 mini computer that is now in the care of AJ over at Forgotten Machines. Now, that machine had a full CPU, 24 kilowords of memory, and then a slot saver IO card that had 2 ports on it. Now, what it used for big storage was an external tape drive. So what we're going to do on this one instead is, well, we've only got 6 kilowords of RAM, which is half of the Data General Nova, but 6 kilowords is still a usable amount. But we're going to have 2 serial ports, one at 300, one at 1200. We're going to have an extra serial port dedicated to a mag tape drive. And then we also happen to have a parallel port that can go to a printer. So I think we've actually achieved a little better I/O capability than the Nova 1210, even if we're a little low on RAM. But because this thing is ticking along at 3 megahertz, I think it's going to be quite comparable to the Data General Nova 1210, which is pretty awesome. It means that I will have effectively built a homebrew mini computer. I am over the moon. So I want to thank you all so much for hanging out with me today, and I hope to see you in the next one.